introduce Tony Kwasnica. I'll tell you some important things about Tony. He's an Arizona Wildcat. That's important because March Madness is coming up.
I don't know, it's not looking so hot.
Well, that's true. But you never know.
So I'll have to fall back on his work.
Uh-oh. Yeah, that's bad. And then,
we're in real trouble now.
And then after being a Wildcat, he decided to go to a trade school up in Pasadena, Caltech. Decided to go to the cold weather from Arizona to Southern California to Penn State.
It's all downhill.
Yeah,
I like going to places that people confuse. You know, so at Caltech, everybody outside of Caltech confuses Caltech with Cal Poly. And Penn State, you know, my parents thought I worked at Penn for a number of years, or lived in College Station.
Well, at least it's not Penn.
Yeah, well, yeah. Nobody confused it with that.
Okay, so, well, Tony's going to talk about auctions. He knows a lot about them. And today's talk is really somewhat of a design choice to see the benefits for both either the seller or the buyers in a particular setting. And it's an interesting set of experiments. That is, what, round 3 in management science?
As of this afternoon.
Okay. So anyway.
Great. Thank you, and thank you for the invitation. I've so far enjoyed my visit, and I'll be around for another week. So if you're interested in chatting about this or any of the other stuff I'm involved in, or even stuff I'm not involved in, I'd be happy to talk with you, because that's obviously one of the reasons I'm out here. And I don't have my kids here, so I have nothing but free time. So this is actually joint work with a former student of mine, Andrew Davis, who's now at Cornell, and a former colleague of mine who's now at UT Dallas, Elena Katok. Maybe one way to think about the genesis of this experimental work is this is actually a series of papers, actually, that Andrew has also been involved in, that Elena and I have on an issue that sort of frustrated her and led to some interesting discussions and therefore led to some papers. Elena is an operations management faculty who does a lot of experiments, but is not in the traditional sense an economist. We'll forgive her for that, I guess. Obviously, as Dave pointed out, I'm trained at Caltech under the likes of John Ledger, who of course taught me well in issues of mechanism design and the sort. And she would frequently come back and she writes lots of experimental papers about auctions and procurement and the sort, and would frequently come back with frustration about sending some of her work to journals, particularly economics journals, because the comment would be frequently by the referees would be, well, this work is all well and good, but we clearly know this is what you're looking at is not the optimal auction, and what would happen if we ran the real optimal auction in this setting? And her comment was, who really cares about the optimal auction? What we want to compare are real auctions that are used in practice to get a flavor for whether or not what works and what doesn't work. And of course, my comment was, of course, the optimal auction and mechanism design is an important tool to help us understand what sort of mechanisms we should be using. And therefore, we sort of got into a discussion, and therefore a set of experiments that in some sense tries to deal with the issue of how good is auction theory, particularly mechanism design sort of theory, in describing what sort of normative outcomes there are in a variety of auction settings. And so, for example, we have a paper looking at whether or not real human auctioneers set reserve prices like standard auction theory says you should, and of course we find not. And this is, in some sense, a contribution to this ongoing work that Elena and Andrew have been involved in as well. So, and obviously I'd be happy to take your comments regarding what's happening. One way to think about what we're doing here is that, well, there's the sort of the standard auction model of people bidding in auctions and environments. There's two common features that is not typically modeled in the auction environment, but are actually, we think, are quite common in a lot of practical settings. One of which is that in many cases, well, there's lots of stories of, arriving in the auction and paying to bid and having to put time into bidding. Frequently, it's also the case that actually determination of your valuation is in and of itself costly. To give you a few examples, certainly the motivating example of this paper, at least when we started on it, was thinking about high-value merger and acquisition auctions. If you think about a firm deciding to bid on this, the example I frequently talk about is, imagine, over the past few years, Microsoft has thought about buying out Yahoo, and now, of course, Google has thought about it. I don't know if they ever actually consummated the deal or not, but certainly there's been a variety of firms that have looked at buying Yahoo. And if you're Google and you're thinking about buying Yahoo, you of course got to put some time and effort into figuring out what Yahoo's really worth. And that's costly to figure out. Maybe a little closer to home if you live in Pennsylvania is thinking about forestry. Certainly to decide what you should bid when you're bidding on timber tracts, you got to send somebody out there to determine something about the relative abundance of various types of wood in the forest. Maybe better for Southern California or any environment is if you think about home buying. And how do you decide how much you're willing to pay for a house? You got to do a lot of things. First of all, you got to go see that house. Second of all, you might want to look at comps to see what other houses like that are selling for. And finally, of course, if you think you want to make an offer on the house, you should have a home inspection to discover some of the other issues. Those things are all costly and time-consuming. And that's the kind of environments we think are obviously worth looking at, and we're going to study here. And then, of course, the second feature that is actually quite common in most realistic settings is, in reality, bidders arrive asynchronously. Not everybody's there at the same time. Right? Now, standard auction theory, of course, assumes that there's a set of end bidders, and the end bidders are there at the beginning of the auction. But in reality, as we know, all you got to do is look at home buying. Of course, buyers come in sequence there, eBay, and so on and so forth. The set of buyers may be developing over time. And of course, we're going to look at a particular instance of that. So, sort of what we're interested in is, given that you have these new added elements, which is that in order to figure out what you're willing to pay, you got to pay something up front to do that. Given that now bidders might arrive asynchronously, in particular, we're going to assume one bidder arrives before the other, what do you want to do as an auctioneer? And if you think about it, there's a couple of different options, or a number of different options, of which we look at a few. One is, if you think about yourself as a seller, if I know that this bidder that comes along early might be willing to offer me something, should I allow them to make an offer early on? Or I should say, wait till the second bidder, who I know, of course, is going to come along before you go ahead and make me the offer. From an efficiency standpoint, you might actually prefer, as the social planner in some sense, that an early deal be consummated, because after all, there's some cost associated with the second bidder coming along and having to learn his or her value, which, although that value might be higher, we of course should consider the costs associated with that. Likewise, maybe on the other side, should the seller decide, well, I'm going to wait, I'm not going to accept any offers or accept any bids until all the relevant parties are here. And in some sense, we can think about that as what we'll call an auction, where we wait to run the auction until everybody's there. Okay? So we're going to refer to these sort of two different potential design choices, which I'll, of course, give more detail to, as one is what we'll call the sequential mechanism, where you give the early arriving bidder the opportunity to make an early offer that is public and known. And then we'll refer to the system where you say, wait, let's go ahead and wait till all the competition is there, and we'll refer to that as the auction mechanism. Of course, the advantage potentially of waiting is that you could, of course, encourage competition between the bidders, and that might be good revenue enhancing for you as the seller.
But in your paper, don't you, the sequential one is guy arrives, first guy, whoever it is, arrives, makes an offer, publicly known, and then you run the auction if the second guy shows up.
If the second guy shows up, yes. So there's always, there's always the option.
You don't just accept the offer.
No, we don't. And so of course, that's one area where we're a little different from, for example, you think about a housing market. I think actually housing is has some similarities to the types of things we're thinking about. There frequently, the first arriving potential buyer makes you an offer, and you get the choice of accepting or rejecting. Here we're going to assume you always still wait to see if somebody else comes along. Now, one of the things that's difficult empirically, as we'll talk about the theory of this, is if you look at this in empirical data, of course you end up accepting our offers in the sequential mechanism under in equilibrium. The only offer you ever get is the first offer, which of course you end up accepting. So it empirically looks like you take the first offer you get, which we have the ability, of course, in the lab to control for that and see if something else does that. But yeah, that's a good point. I mean, we have certainly restricted the set of mechanisms and institutions available here to be of a particular type, and of course there are many interesting choices one might examine going forward, and we are looking at only a particular class of certain choices. And there's a few reasons why, one of which, of course, is the previous theoretical work. So let me give you a little motivation about this from really 3 dimensions. The first dimension is empirically ask yourself, what is sort of, what are people doing? And I think maybe the best way to think of it, and once again motivated by issues of mergers and acquisitions, is, Warren Buffett once famously said, we don't participate in auctions, period. Right? So certainly there's a perception frequently, particularly often by buyers, that if you have an auction-like situation, it's to your disadvantage. Right? On the other hand, there seems to be some preference by sellers for an auction-like mechanism. On the other hand, both exist in many contexts, sort of even side by side. In the location of mergers and acquisitions, there's something more recent that's recently come out called go shop provisions, where an early offer is made to a firm, and then sort of the way the rules are written is they have the ability to solicit later offers by newly arriving firms. So, Microsoft first makes an offer, a tender offer to buy Yahoo, and Yahoo can sort of wait to delay to see if Google's going to come along and make a competing offer, which is essentially more like an auction. Right? Likewise, I think in home buying, well, in the United States, it's very much a market where that looks a lot like a sequential mechanism, right? Basically one person comes along, makes you an offer, you accept or reject it, so on and so forth. On the other hand, with today's housing market, how are most foreclosures dealt with? They're actually dealt with in an auction setting. Right? Likewise, my former dean and current colleague Ken Lush actually has a really nice article that points out in Australia, a large number of private real estate sales are actually conducted both by auction, but another about half and half are run by auction, and the other half are more on the course, we implemented as sort of an ascending clock auction or English auction. So the theory is quite straightforward here. Of course, given that the second stage triggers an auction, we all know what should happen in the auction. The problem now is basically the first stage entry decision of the two bidders, so that they have to consider the cost of entry C and, of course, their expected revenue. They don't, of course, at this point in time know what their value is, so they have to expect what their value is. So, if you think about it, what you can find out is that, of course, upon entry, if both bidders enter, the expected profits for any bidder is 1/6, given the uniform distribution. Of course, if there's only one bidder in the auction, you get your whole value, because the price is 0. But of course, not knowing what it is, the expected value, that's a half. And of course, nobody enters, nobody gets anything. It's straightforward to see that as long as the cost is less than 1/6, it is a dominant strategy for both bidders to enter. Right? So in this case, costs are reasonably small, less than 1/6 the total value, maximum valuation. Then it's a dominant strategy for both bidders to enter, and of course that should trigger a standard auction, which of course has all the nice flavors of an auction and yields an expected revenue to the seller of the bid. Okay? So in this case, as long as cost is sufficiently small, the auction should be basically unaffected by this cost of entry, cost of learning your valuation treatment. The sequential mechanism requires a little more explaining. Okay? So let me give you sort of a timeline of events. Okay? So, as I said, bidder 1 arrives first, and they get to decide whether to enter or not. Right? If they enter, they pay a cost C, and they learn their value. Then, prior to bidder 2 arriving, they have the opportunity to place a preemptive, what you might sometimes call a jump bid, of something other than 0. So it's assumed, of course, if they don't place a preemptive bid, it's just a bid of 0. It's a standing bid of 0, essentially. Right? The key is, of course, this preemptive jump bid is publicly visible to bidder 2 before they decide whether they enter the auction or not. So they know that this bid is, let's say, 5 or 7 or 23, and bidder 2 arrives and say, well, the bid's 23, do I still want to enter? If they decide to enter, of course, they learn their value, and then, of course, now there's 2 bidders around, we trigger an auction that starts at essentially the preemptive bid, whatever it might have been. Right? If, of course, they decide not to enter, right, then, of course, bidder 1 wins the object and whatever the preemptive bid was. So the preemptive bid is, of course, assumed to be binding. They can't go back and say, wait a second, now bidder 2 is not there, let's lower the price. They have to, of course, stick to their preemptive jump bid. So you can think about this as just one round of an English auction before the other bidder gets there. This is sort of another way to think about this sort of mechanism. Okay. So what should happen in theory? The tricky part, of course, here is to think about what happens once bidder 1 arrives and they're thinking about this preemptive or jump bid. In order to describe the incentives there, it turns out that in equilibrium, the preemptive jump bid is going to have to look something like the following. Is that if they have a low value, they're going to place no preemptive, right? I mean, in other words, they learn they're probably not very high value. They're not a high valuing bidder, so they have very little incentive to place a preemptive bid. Right? On the other hand, if their value is in some sense high, they'll want to place some sort of preemptive bid. Of course, the tricky part in the theory is determining what these 2 values are, in other words, what the amount of the preemptive bid should be, and of course, who should place the preemptive bids. Okay? And the critical thing to notice here, let me try to describe these amounts to try to give you a motivation for the way the theory works. We're going to determine this P star, which is the amount of the preemptive bid, and we're going to call that the preemptive bid. And this VS, which is the cutoff, or between where all low bidders with values below that say, screw it, I'm just going to bid 0. All bidders with values above that say, I'm going to bid this preemptive bid. We call this the deterring value. Okay. So let me describe to you.
So let me see so when the first bidder arrives, he hasn't paid the cost to find out his value yet?
He arrives. Once he arrives, we call entry and arrival. He arrives, he decides to enter. He's paid C. Right? So C's a sunk cost.
So he doesn't have the choice of not arriving.
Well, once he's entered, he could choose not to enter.
And you have that option.
Yeah. He could choose not to enter and not learn his or her value, and basically go home.
As opposed to just bid zero.
Yeah, they can't, I mean, they don't have an option, once they don't enter, once they don't pay for their value, they can't pay. Right? So we don't let them bid ignorantly in some sense. Right? So it is a cost of entry, and upon entry you learn your value.
Okay, so but you can't do the following. You can't say, well, I'm just going to put it zero and hope for the best.
No. That's an interesting, I mean, you know, maybe I'll just wing it, right, and see what happens.
One, and I know that's it's a pretty good case that I have a value greater than.
I mean, one way to think about it is, you know, you in order to some sense even decide whether this thing is for sale, you need to do your due diligence, right? I mean, you know, it's costly for me to, if I decide I want to go buy a house, you know, I got to go visit houses, just go talk to a realtor, all those sorts of things, all of which are costly for me even to start to figure out what the values of houses are, right? And I couldn't, you know, just wing it without, you know, paying some kind of cost. And of course, there might be an interesting extension to think about, you know, to those houses.
In the days after the previous housing crisis, when the government was selling these properties, there were guys going around bidding the low value on all the properties that were available that day.
Without even looking.
Without even looking at them, they just went from auction to auction.
Yeah, and that's not an option. I mean, and that's really to be consistent with the theory that's been looked at. It's basically the story of, you know, entry is costly, and along the way to entry is learning your value.
I just wanted to know what the
Yeah.
Okay.
Good question. So let me describe how the theory describes how these values should be picked, or the theory describes how these values should arrive via equilibrium. So the deterring value is actually in some sense critical for bidder 2, and the preemptive bid amount is in some sense critical for other bidder 1s, right, in terms of this equilibrium. So think about the following. The deterring value, Vs, which is that cutoff between essentially low valuing first bidders and high valuing first bidders, is the amount that a bidder 2 that arrives, hasn't paid his or her cost of entry yet, sees this preemptive bid of P star and says, look, I know I'm competing against bidders with values greater than Vs, right? So I don't want to get involved. Right? Matter of fact, the way that this amount should be set in equilibrium is the deterring value is exactly the value that if I'm an entering bidder and I say, wait a second, I know that the bidder I'm competing against has a value Vs or greater, right? I'm exactly indifferent between competing against, paying my cost and competing against him or her, or staying at essentially the expected value of participating in the auction, given that it's now a high valuing bidder I'm competing against is 0. Okay? That's how the deterring value is determined, right? Now, what is the role of the preemptive bid, right? Well, the preemptive bid, essentially, if you think about a signaling equilibrium, right? In any kind of signaling equilibrium, you have to, as of course a high-valuing bidder who wants to place the preemptive bid, keep out low-valuing bidders from pretending to be like you, right? Bidder 1s in this case. Right? So the preemptive bid is exactly the amount that makes a low-valuing, a value below Vs, bidder 1 say, look, it's not worth my time. I'd rather trigger an auction against a bidder 2 than to place that relatively high preemptive bid, and, you know, even though I'm going to win it for sure, win the object for sure for that, because of course if I place P star and Vs is greater than P star, I know that bidder 2s will not come into the auction. Right? I'd rather just play in the auction because my value is simple. Right? So critically, P star is really determined to make low-valuing bidder 1s not want to glom on to high-valuing bidder 1s, right? Whereas the deterring value is sort of separated to keep bidder 2s out of the auction if they see a high value.
Is that high enough so that you wouldn't get somebody to do this to resell?
Well, we obviously don't allow resale.
But if you did, I mean, you're going to have to resell it to the guy you're now outbidding with this preemptive.
Yeah, I mean, I have to think about that. I mean, obviously, resale is an interesting issue, and this sort of has a flavor of some of these resale stories. I have to think about it. I mean, so you'll see what the amounts are. They're pretty high, right? So, matter of fact, let me give you a little picture of the theory here, if I can. I can't do that by my point you thing. I'll resort to the. I think it's worthwhile to sort of give you a story. So here's bidder 1's calculations. I think this is maybe the easiest way to see this. is, you know, think about it this way, is P star, right, given whatever P star is, this is essentially, the red line is the value for a, you know, where value is on the x-axis here. This is the expected profits associated with placing the preemptive bid P star, assuming it completely deters entry by bidder 2. So, for example, if I got a value of 0, well, yeah, I mean, placing a P star about 4 seems like a good idea because I win for sure. On the other hand, I have a value of 0, so I lose 40 cents for sure, or 0.4. Right? On the other hand, the blue line is essentially, given my value, the expected profit from competing in a standard auction versus one other bidder. And of course, what you can see here is the deterring value is essentially set by where these two lines cross, right? Below that, I don't want to compete. Above that, I want to place the preemptive bid. Okay? So that's essentially how the theory results are determined. One way to think about this is, given that what you're deterring is entry or not entry, there's no way to sort of separate the other bidders more via some sort of signaling equilibrium, because of course once you've placed a high enough preemptive bid or have a high enough deterring value, essentially bidder 2 is going to stay out. So there's no way that a really high value bidder can do anything more other than to basically discourage entry by bidder 2.
So it looks like that price is above a half.
In this case, this is the example for the low cost case where, yeah, it's above. It looks like this is above, but the preemptive bid is about 40. In the low cost case, is about 40 cents. We'll talk about what the other equilibrium.
And bidder 2 can learn whether there is a preemptive bid.
Yeah, they learn the preemptive
without cost.
Without cost. Yeah, they see it. It's posted. Right? So they know someone made an offer for the house, right? Or they know that you know. I think that's where, you know, they know that. Google knows that Microsoft has placed a tender offer for Yahoo, right? And about how much it is, now do we go and investigate whether or not it's worthwhile for us to do it, right? That's sort of the things that are, of course, frequently it's not really public. And that would, of course, be a different.
It's not costless.
It could not be costless, but of course, you know, as with any model, I mean, all these things would change the structure. So there's a description here to give you a brief. How do the equilibrium values, how are they affected by changes in the cost? Of course, if the cost goes above 1/6, you know, all these equilibria are out the door, so we're assuming costs to be relatively small. And, you know, not surprisingly, you know, as the cost of, you know, so the low cost case is somewhere over here, you know, the deterring value of around, you know, preemptive bid around 40 cents and a deterring value somewhere above, you know, 60. But of course, as the cost gets higher and higher, of course, both these values go down because, of course, you know, it's harder and harder. It's easier and easier actually to deter entry. Right? So when cost is really, really high, you don't have to do a whole lot to keep bidder 2s out because, you know, the cost is so high they practically don't want to compete anymore. Right? On the other hand, when the cost is 0, essentially they'll enter no matter what you do. Right? And of course, that impacts the expected revenues from the two different mechanisms. So the auction is sort of, no matter what the cost is, going to yield you 1/3 of the value. On the other hand, the expected revenue from this sequential mechanism, as described, is declining because, of course, if the cost is high enough, you basically, you know, show up and place a very low preemptive bid, and you deter entry by the second bidder, so that this expected revenue goes down as cost goes up. Right? And that's a little story of total bidder profits, which behave. So that's the mechanism. Of course, the real result, in some sense, of Buelow and Klemperer is to show that this equilibrium, as I described, is the unique. But there's actually really an infinite number of signaling equilibria of this nature here. But they, of course, show that it's the unique equilibrium satisfying essentially the D1 refinement, which really means it's sort of profit maximizing for the bidder 1s. In this case, because really almost any cutoff strategy, with step function strategy like this, could be rationalized, given the fact that you have control over beliefs, essentially, could be rationalized by some kind of beliefs of bidder 2. If the D1 refinement is what helps tie it down to this particular step function that we identify. So what we want to look at is the prescription, whether or not this theory does well in the lab. So of course, let me talk about some features of our experimental design that we looked at. So as I think I mentioned, we can have 2 bidders, predetermined in fixed order, you know, it's uniform draws. It's not, even though all the figures I do are 0 to 1, you know, of course, we're giving values 1 to 100 just to make it a little easier for them. They're going to compete in 30 periods, but there is a random rematching amongst your cohorts of 6 bidders. So there's some, you know, you're not always playing against the same bidder, but of course, occasionally you are. Notice that there is possibility of losses here because, of course, the cost can be quite high. You can end up getting a low value and therefore losing money. So we gave everybody a fixed endowment of 20 every period to hopefully help avoid the possibility of losses. Conductees at Penn State and only one treatment. I'll talk a little bit. We ran a Holton-Lowry sort of standard, nowadays ubiquitous risk aversion exercise in order to understand whether or not risk aversion played a role. We'll talk about that when we get to the results.
So why only 6 cohorts?
Just the size just worked out. I mean, to work out a little more convenient, and you know, I mean, just that was a choice. Yeah.
Do they receive the results between periods?
Yes. Yes, they know the results and all those sorts of things. I'm not going to look at. There's no real evidence of much learning going on here, so we don't talk about what happens over the 30 periods. But we certainly have looked at it, and period is pretty insignificant. So there's not a whole lot of evidence that things are changing over time.
They only see their history.
They only see their history. So, I mean, issues of coordination among groups. And we don't have, I mean, really, there's not much evidence that's happening here in the data. And notice that was one of the reasons for doing a predetermined fixed order so that, you know, it's not like, I mean, because you could imagine a repeated game strategy where you say, well, you're going to go first this time, I go first next time, and of course, it's sort of it's a self-enforcing kind of inclusive strategy over periods. That's something that we you know, you're always either a bidder 1 or always either a bidder 2 in this context. All right, so what do we look at experimentally? Of course, the 2 main treatment variables we're going to look at, of course, one is the particular mechanism. Ron we'll call the auction, basically we'll call it the auction mechanism, and then, of course, the other one we'll call the sequential mechanism. And then the other thing we're going to vary, as noted by the theory, of course, the cost of entry can have a dramatic effect on what we expect to happen between these 2 mechanisms. So we'll look at one that we call a low-cost environment, and another one which we call the high-cost environment. So just as a note, this is basically the cost is 3, and the low cost is 3% of your maximal value, and in the high cost it's 10% of your maximal value.
Okay, so it's a percentage.
Well, no, it's 3 cents of your, you know, so the maximum value anybody got was 100. So, you know, so it's 3 experimental units. So it's just,
But you said you had an endowment of 20.
yeah.
Why did you need such a high endowment?
Because, well, I mean, because we looked at expectations, it's pretty easy to potentially lose money in some of these, right? So when you're considering, particularly in the high cost setting, you're paying cost 10, that's half your endowment right there.
Oh, it's not each period, it's an endowment at the beginning.
It's the beginning of each period. No, it's the beginning. I give you a separate 20 units every period.
But the most you can lose is 10, right?
No, you could lose more than 10. You pay a cost of 10. Well, I mean, yeah, I guess the most you could lose 10.
Unless I'm missing something.
Yeah, no, I guess the most you could lose is 10. So we're guaranteeing they're making a little bit of profit.
You're just a nice one.
Yeah, we're okay. We'll talk about whether risky behavior should have any impact here. So, you know, obviously it's a design. We looked at, you know, 10 cohorts in each of the institutional choices. So we're treating a cohort of group of 6 as our independent observation in all the analysis we do here. So in order to account for lack of independence amongst the cohort. So let me remind you of a few of the theoretical predictions in number-wise. So what should we expect to see between the auction and the sequential mechanism and the high cost and low cost? First of all, notice the revenue results here. So the seller revenue, of course, in the low-cost treatment, there's not much difference. Right? So there's, I mean, even though the auction should be a little higher, and these are using realized values. That's why they're not exactly a third of value, for example, where these are the theoretical predictions given the values that we drew for the bidders. The sequential mechanism provides a little lower expected seller revenue, but not dramatically so. But of course, once you move to the high-cost environment, the expected revenue is substantially lower under the sequential mechanism in the auction. The reason for that is because of the changes, in some sense, in what it takes to deter entry by the second bidder. Here, in both cases, a first bidder should always enter. once they enter in the low-cost treatment, they basically place a preemptive bid of 41, which means only if they have a value greater than about 57. Okay? Well, of course, that happens a little less than half the time, right? But the amount they're placing the bid of 40 is not too bad as the auctioneer, and therefore the revenue from the sequential mechanism is not all that different. On the other hand, under high cost, it doesn't take a whole lot to keep the second bidders out. Matter of fact, any first bidder with a value of about greater than about 22 should place a preemptive bid, and only a preemptive bid of about 20, and so therefore, about 78% of the time, approximately, a bid of 20 is going to be what the auction ends at, or what the mechanism results in, which is obviously a lot lower than the expected revenue from triggering an auction about 30.
Just a point, so you don't want to lock down bidders?
Yeah. What's it?
So in mergers and acquisitions, the firm that's to be acquired will actually pay the second bidder their due diligence
Yeah,
process.
well,
and that
that would fight this, right? That's actually that's a nice example. That'd be nice to, because that's exactly what you can imagine they're trying to stop happening here. Particularly because you imagine, like
Those are the recommendations in these, like these books like Co-op Petition, Elba, Brandenburger and Elba, they pay someone to come in to make a bid, look at it and that sort of thing.
basically a shill. I mean, it's not a shill bidder, I
No,
guess.
it's not, but
It's somebody to lower the
You're
cost
paying
of
them
that.
to get in, right? To create some competition. And this, one story of this theory model would be that that's what you want to do, right? Because of course, if they know they can deter entry, they're going to place a bid and they are going to successfully deter entry. Right? Now, on the other hand, if they know you're going to do that, they should never place any kind of. I mean, if you know that the seller is going to respond by paying essentially the second bidder to come along and do it, then you should never bid anything in the first step to the equilibrium. It's sort of easy to follow. And if you know they're going to enter, why do anything that's costly for you anymore? So let me give you a result summary. I mean, this is hard to read, so it's probably easier to show the pictures. Right? So here's the major picture, I guess. Let's compare the observed revenue for the seller of the theory versus the data. So the theory, of course, this is the theoretical predictions for the different cost treatments for the sequential mechanism, and of course the auction is flat as a result of that. And of course these are color-coded correctly. This is the observed seller revenue, average seller revenue for the sequential mechanism, and this is the observed seller revenue for the auction. What you can notice, of course, is first of all, as opposed to theoretical prediction where red is always greater than blue, here, of course, blue is always greater than red, and these differences are significant. So the sequential mechanism in the laboratory always generates significantly higher revenue than the auction mechanism. Now, the good thing for the theory is, of course, there is a decline in the revenue from the sequential mechanism as a result of an increase in the cost. On the other hand, there's also a decline in the auction revenue as a result of the increase in the cost. And of course, the theoretical prediction is that those changes in cost shouldn't really impact the revenue in the auction. Okay? So we see a decline there, which of course is there. But of course, our major, we think, major result is that essentially these colors are flipped. The theoretical prediction is always sequential mechanism below auction, and of course, we get something that's substantially different for both of our cost treatments. So let's, in words, really what this says, seller revenue is always higher in the sequential mechanism than the auction. Seller revenue in the auction is, of course, lower than theory. So one thing to think about as we try to figure out what's going on here, notice here that generally speaking, the auction is doing worse than the theoretical predictions. Right? It's not attaining the full revenue. Whereas the sequential mechanism is always generally doing better than the theoretical predictions in terms of revenue. And of course, we do see the qualitative difference. The cost seems to matter in both treatments, where it shouldn't in the auction. Okay. Similar things can be said in terms of bidder profits. Remember, on the bidder profit side of things, bidders should prefer the sequential mechanism. At least bidder 1 should prefer the sequential mechanism because it allows them to eliminate competition. Bidder 2 should essentially really prefer the auction. What we generally find is that in the auction mechanism, bidder profits are not. I mean, it's pretty much what theory says. I mean, we can't reject that they're different than theory. On the other hand, when we look at the sequential mechanism, bidder 2 profits look about what the sequential mechanism predicts they should make. The people that appear to be the big losers in terms of comparison of the theories, bidder ones. Bidder ones are making far or significantly less than what's predicted for them to make under the sequential base, which seems to indicate they're somehow not being able to take advantage of their sort of advantage position in this mechanism, which is coming first and having the opportunity to potentially deter entry. And what we want to figure out is what's driving, what appears to be happening that's leading to this lower profit for them, which of course in turn is eventually leading to greater revenue for the seller.
Can you go back to the figure, the difference? Yeah, there's nothing there. I can't tell. What are the levels? What's the difference? They might be significantly different, but do you know?
Well, I mean, we're talking, so, you know, this is 0.3 to 0.4, remember, values between 0 and 100. So, you know, I mean, it looks like it's somewhere in the, oh, we can actually look here. It's in the table, right? So the average performance on the revenue, 6 to 30, 31 to 34. So there's not a huge difference. I mean, it's not, you know, it's enough to give us statistical significance. Yeah, the difference gap is not, you know, I mean, we of course would have expected the gap to get bigger as the cost, I mean, the cost of 10 is really pretty darn high here. So it is kind of a bit, you know, interesting to see what's going on here, and that's one of the things we want to look at. So let's see what happens. So what we really want to start thinking a little bit is individual behavior, right? So what are individuals doing here that appears to be affecting the results? So let me give you a brief story, and then we'll kind of go into this. Is one of the things we know when we look at this is, remember, in theory, of course, given that the cost is below 1/6, it's a dominant strategy for all the bidders to enter the auction. It turns out that in the auction stage, bidders fail to enter 100% of the time. They enter with a very high probability. Matter of fact, where's the entry here? In the, here's the entry proportions. I mean, they're pretty high, but, you know, even in the auction, you know, down here it's, you know, in 80s and 90%, right? So, you know, about 10% of the time, or even greater than 10% of the time, they're not entering the auction when they should be. They have a dominant strategy of doing so. Of course, what does that do? It means that whenever one bidder doesn't enter, it has a very asymmetric impact on seller revenues because, of course, you know, no bidder is going to pay anything when there's only one bidder there, so the price is zero.
If you
and seller
take
revenues.
the experimental overbidding that occurs in private value auctions,
So-
that explains that. That explains.
So there is no experimental overbidding. Given, matter of fact, I think,
Standard private values auctions.
so we are not running a first price sealed bid auction here.
Oh, I see.
We are running this as an English auction, English clock
Oh,
auction.
it is, okay.
Our behavior here is, matter of fact, one of the things we want to be sure we replicate as we talk about alternatives here is I think there are 3 instances, it's some very small number, where we actually see differences with the theoretical predictions of the English auction. So basically everybody stops at their value and does a bit above, which is, of course, we know that experimentally they do tend to behave as expected. And the reason we did that is we really, you know, don't want this end up being an experiment on our people misbehavior in the first price auction, essentially driving earlier behavior. On the other hand, as we start talking about what kinds of theories might rationalize our data, we don't want to come up with a theory that would subsequently change how you would want to bid in the auction because we know that experimentally it didn't. So that people didn't, you know, people basically followed the standard theory in the
So the
auction.
story here is that the second bidder, or at least in the auction case, somebody fails to enter.
Both of them failed to enter with some frequency.
But sometimes only one guy enters.
Yeah.
And therefore the revenue.
Most of the time, if it's
And the revenues are going to be very low.
and that's what. So notice So one way to think about this. You know, when you think about it, even theoretically, that the only way you could err in the auction, right? Given that we think people are going to bid up to the right value in the auction, in the entry phase, is always going to have a negative impact on revenue in the auction. On the other hand, the only way you can err in some sense in the sequential mechanism is over entry, because remember, bidders who should never enter,
Right.
and of course entry triggers more revenue.
Right.
So
Did you measure? Did you go and to calibrate or some preferences according to the risk preferences that you elicited in order to see?
yeah, we'll talk about
Okay.
But here's the thing, is that what I'm getting at is that you're telling me that the theory is that they should always enter in the auction phase.
Yes.
Both guys should be in.
Yeah.
The fact that somebody does it that has a real strong effect on a zero revenue. So if you make a conditional on entry, do those numbers change?
I'm sure it does.
So a conditional entry, you do worse. I mean, the seller likes.
Sure, probably.
Right.
I mean, I don't know if it's enough to switch it. We have to
Well, you're
check.
getting zeros then. That's not
Yeah, no, that's true. But I'm not. I just, without having looked at the data, I don't want to be. But on the other hand, we know they don't do it all the time. So I mean, we want to figure out why they are when they should theoretically be dominant strategy.
I'm just,
Right.
the suggestion would be that you get this because these are two-person auctions, and
Yeah. No, an interesting question is what happens exactly.
Too many times you get Steve Rossetti
Yeah.
in the auction.
Yeah.
He needs to sleep. Is that right, Steve?
Yeah, so is it just I mean, let's think about what's, I mean, what you'll see our theory.
It's not the same guy not entering.
No, certainly the fact that we looked at 2 makes this much the impact of that more
Yeah.
dramatic. But then again, if you're going to propose a theory that says you should pick one, always pick one over the other, even in the simplest cases, you would think the theory would have somewhat correct predictions, and we're coming up with a theory that is quite different than that. And one easy way to see that is the auction revenue is always negatively impacted by under entry, and that's the only thing that can happen is under entry, whereas the sequential mechanism is always positively impacted by over entry, and that's one of the ways that you can think about it. Let's look at these preemptive, what happens in the sequential mechanism, because that's sort of, I don't want to say the more interesting case, but certainly the case that we're interested in thinking about. So this picture is maybe not the easiest always to see, but here's the idea. So what we want to do is try to put together the theory and the data. And so the theory is the dashed lines, and the data is the observed behavior. And so first thing we want to look at is, is it basically only low valuing bidders that aren't placing preemptive bids? Theory says, look, if your value is low, for example, in the high cost treatment, if your value is below 20, right, you should always place a 0 bid, and above 20, you should always place some kind of positive bid. Right? Notice, of course, what we see is in both treatments, basically, even bidders with high values are frequently not preemptive bids. Right? About, somewhere in the order, it's pretty stable, around 50%. Certainly low valuing bidders here figure, hey, I shouldn't place a preemptive bid because I have no value for this thing, why would I do that? But on the other hand, even with quite high values, about half of the time, across both treatments, you're placing no preemptive bid. Okay? But that may not be irrational. Right? I mean, it's one thing that is, one way to think about this is a really irrational behavior, because, of course, we got to think about what, of course, bidder 2s are doing in response to the observed behavior. Bidder 2s, for example, are always entering. I might as well always place a 0 bid, right? So you got to be careful about some of the presumptions you make. So here's the other thing. Let's suppose you do decide to place a preemptive bid. What should you do? Of course, theory says, basically, that your preemptive bid should look like the step function. Either it should be 0 from here and then jump up to a high amount. Right? It's critical, of course, in the theory that the preemptive bid look like this, because you can't have, in the theory you looked at by Buell and Klumper, under their model, you can't have a revealing bid function. Right? It wouldn't be an equilibrium. Right? Because, of course, high value bidders would say, this isn't worth it for me to tell you that my value is 1, I might as well look like a lower value bidder. And vice versa, low value bidders should say, why should I tell you my value is low when I can just tell you it's 0, essentially. Okay? On the other hand, looking at, of course, the averages, notice that on average, essentially the preemptive bid function looks like it's basically an upward sloping line of the bidder's values. So, of course, if bidder 2s are smart, in some sense, they should be able to sort of back this out and figure out essentially a little more information about your value than essentially the step function. Right? Now, let me point out, though, that, of course, this is looking at aggregate data. It's worth asking whether or not individuals look this way. Because it might be that what we're looking at here, the way we're failing is that all our individuals are following sort of step functions, but that in aggregate it looks like a revealing bid function. We look at the individual level data, essentially it's no different. Basically, there's only like 3 bidders out of all bidders that look anything like a step function here. So it's quite, and I think 2 of them are ones that never bid anything. And they always place a preemptive bid as 0. In which case it's technically consistent with one of the perfect Bayesian sequential rational equilibria here, just not the one that satisfies the D1 refinement used by Buell and Klumper. Okay. So there's a lot of things going on. So going back to the question of, well, we really got to think about what how are bidder 2s responding to this information? Because if, for example, they don't respond, they enter anyway. In some sense, that goes back to the comment about, paying somebody to bid for you, paying a second bidder to come along. You should, of course, not place a preemptive bid. So maybe it's perfectly rational for them to place lots of 0 preemptive bids. Well, let's see what bidder 2s do. So notice here that above, depending on the cost treatments, essentially, as they see high, that essentially any preemptive bid below here, they should essentially always enter, and then, of course, anything above they should never enter. Okay. And notice what we see, of course, is we do see declining entry rates with higher preemptive bids. On the other hand, for quite high preemptive bids in these ranges here, we see actually fairly high entry rates by bidder 2s. And some of these little blips over here, you want to be a little careful how much you make out of this, because of course there probably was like one observation with a preemptive bid at 80, because who's going to really place a preemptive bid at 80 in the auction stage? That's a pretty high preemptive bid. But in these ranges, in this 40 to 50 range, one way to think about this is if you look at this data here, this is essentially even with the most optimistic beliefs a bidder 2 could have, which is that preemptive bid is essentially the value of the first bid, right? And that's the most optimistic view you could have about the preemptive bid. Right? In this range, they'd be guaranteed of losing money in expectation they would lose money by competing against a preemptive bid of above 50. Yet they still enter about half the time. Right? So there's actually quite a bit of entry associated even at high-end preemptive bids, which might suggest that if bidder 2s are going to enter anyway, why ever place a preemptive bid? Okay. But of course, we see some of that, but we don't see that all the time. So what we're interested in is trying to figure out what's
Let me see if I got this right. So I'm always a bidder 2.
Okay.
Right?
Yep. Yep.
And so there's 6 of us, so there's 3 bidder 1s.
Yep.
And I got 30 rounds, so
Yep.
I'm about to visit them 10 times.
Yep.
So I'm a bidder 2. Would I be actually willing to go in and lose money? A bid, go into the auction, even though my value is going to, even though I see this number here, that I think that I'm going to lose money by going in.
Why would you do it?
Because I want to let these guys know I'm going to enter. And if they know I'm going to enter, they're not going to do these preemptive things. We'll just...
Okay, it's perfectly possible. Now, we don't see, we look for whether there was some sort of learning effect here. So one would expect that would mean preemptive bids should be going down to 0 over time if bidders are doing that, right? Because of course, now I see over entry, I know they're always going to enter. As a first bidder, a rational response by me is to not place a preemptive bid because it's costly for me to place a preemptive bid, right?
Yeah.
We don't see a decline.
But the fact that it's not that means that they know that these people are going to be doing this, right? In other words, it's not a learning thing. You go, well, hold it. If I was a person too, I might do this since I'm going to be visited. If I was going to do it, I would. They know I'm going to enter, and the first guy going in knows it's going to enter. So,
but that's not what they're doing, right? I mean, they know they're going to over-enter. That's true. I mean, they do. Now, but it's critical to remember: bidder 2s do respond to preemptive bids, right? They do enter less as preemptive bids go up, right? And of course, the critical thing is preemptive bids. Well, frequently 0 or not always 0, right? So if you know they're going to enter all the time, of course, you would never want to place a preemptive bid. We're somewhere in between that, right? Is that there's a fair amount of entry, but there's also a fair amount of non-entry, and that non-entry does appear to be responsive, right? In a relatively strong sense, right? To the actual preemptive bid observed, right? So, I mean, I grant you that. And of course, there's lots of things going on. But here, I'm here entering when at least in the theory, I'm losing money as a result of entry, and I'm guaranteed almost to lose money as a result of my entry.
Okay. That's when I asked you at the beginning why 6 people. Now I sort of understand that you wanted to make sure that your observation is the cohort, as opposed to bringing in 30 people.
Yeah.
Right,
okay. So let's we want to try to figure out. So clearly, this is inconsistent with Buell and Klemper's model, which which maybe isn't all that surprising. I mean, in some sense, one argument we're making here is Buell-Klemperer's model, by identifying this particular perfect Bayesian sequential rational equilibrium, is a very knife-edge case, and it requires a very strong notion of understanding beliefs here. Because notice, what are you as a bidder 2 supposed to do here? You're supposed to observe that preemptive bid and be indifferent between entry and not, and choose not to enter. Okay? Which you could say, well, I'll just choose to enter too, or I'll choose to enter half the time. Okay? Both of which, of course, would have impact on the revenue. Okay? So what we want to look at is sort of what are some models that might help us organize and explain behavior in this setting. And so we want to look at a few, obviously starting with the simplest in some sense. We'd be happy if we could explain the JA using that. Of course, that might be risk aversion. So is risk aversion a likely descriptor reason we see what we see in the laboratory? And I think we can pretty confidently say no. This probably isn't quite as clear as we'd like. So let's think about it first theoretically. Okay. So in the sequential mechanism, risk aversion basically should always lower the revenue from the sequential mechanism. And here's why. It's easier to do so. Remember, now if you're thinking about this as a choice between a risky prospect, which is participating in the auction, or a certain prospect, which is not participating, right? Of course, as you become more and more risk averse, you're going to more and more go for the certain prospect of not participating and avoid the risky prospect of participating in the auction. Remembering, of course, risk aversion should have no impact in the auction we ran, because, of course, we're looking at English auctions where it's a weekly dominant strategy for you to bid up to your value, so risk aversion should have no impact on it. Whereas, of course, if we looked at a first price sealed bid auction, then we had the confound that, of course, that would have an impact here. Looking, for example, I mean, these charts are for what would happen as we change the risk aversion parameter for constant relative risk aversion preferences, right? And what you want to notice, the 3 lines we have created here is this is actually the deterring value, this is the preempted bid, and this is the expected revenue as a result of that behavior, right? And of course, as you see, as moving over to the right is always more and more risk aversion. 0, of course, is risk neutrality in this case. So risk neutrality matches up to our original predictions, and of course all these numbers are lower as you get more and more risk averse. Okay. What's kind of important to think about here is look at the cutoffs and where this drops to 0, right? So notice these lines drop to 0 here a little, somewhere about 0.7, and here it drops to 0 about a risk aversion parameter of a little under 0.4. What happens to the right of this is worth pointing out. It doesn't mean there's no equilibrium here. As a matter of fact, the equilibrium is really simple. The equilibrium to the right of here is the first bidder realizes all I got to do is enter to keep out a second bidder. A second bidder, knowing that a first bidder entered and placed a preempted bid at 0, says, wait a second, I'd rather the certain prospect of not participating in the auction versus the risky prospect of participating in a 2-person auction, so I'll take the 0. Right? So that actually over here, the equilibrium prediction to the right of these things for sufficiently high risk aversion parameters is 0 revenue. Right? So if anything, risk aversion sequential mechanism should drive generally revenues down. But remember, in our experiment, we're actually observing revenues that are higher under the sequential mechanism than that predicted. The same is kind of true in the auction. So here's where maybe a good story for risk aversion. So remember, the auction behavior shouldn't change, but the entry decision might be affected by risk aversion. Matter of fact, we could say quite easily how. So remember, we said about somewhere in the range of 90% of the time bidders were entering, and about 10% of the time they weren't. Well, it is of course possible, although we could obviously question whether or not people play mixed strategies. One way to think about this, maybe it's just a mixed strategy equilibrium of the entry game. Right? Well, in order for there to be a mixed strategy equilibrium here, you have to basically order the expected payoffs in the following way. So I have to prefer the expected utility from a 1-bidder auction, basically me winning at a price of 0, to non-entry, but of course prefer non-entry to the expected utility from a 2-bidder auction where we compete against each other. Because then, of course, if we go back to our original picture here, probably a mistake to try to do this, Now, of course, when we have it ordered like this, what it means is actually the two Nash equilibria are at these corners. One bidder enters, one bidder doesn't enter. That's the only way, given this payoff structure, we could rationalize a mixed strategy equilibrium. Of course, in a mixed strategy equilibrium, you have to be indifferent between the two pure strategies in the support of the purely mixed strategy. So we can solve for what the mixed strategy equilibrium has to look like. Let me and I can tell you what sort of levels of risk aversion would be necessary to have, assuming constant relative risk aversion. So it'd be about 0.7, 0.5, right? Given the CRA preferences. Which, given what's been observed experimentally, we cite, 0.4 to 0.7 is not all that uncommon in previous experiments that measured levels of risk aversion using CRA preferences. So these are not necessarily all that out of the realm of possibility. So perhaps risk aversion explains the data reasonably well under the auction mechanism. On the other hand, go back to the
Loss
picture.
aversion with respect to beer money.
What's that?
Loss aversion with respect to beer money.
Loss aversion. Well, that's an interesting question.
I mean, if they take 0 as the reference point, they don't,
Yeah. So we're assuming risk aversion.
Not 0, it's whatever they get without spending 0.
Yeah. So, here's pure risk aversion. Of course, loss aversion might do something else here. Of course, you've got to be a little careful because loss aversion might also predict different behavior in the auction bidding stage. And we know that they're there playing their weakly dominant strategy of bidding up to their value. So that's what's tricky. Now, the theory model we're going to propose could, in theory, it's a somewhat reduced form model, and it could be explained by things like loss aversion.
These are students at Penn State.
Yeah.
It's beer money.
Beer money, yeah, it's beer money. Got it.
I know that.
I need my money. I don't want to gamble on. I want to have a couple beers.
Yeah, perhaps. The key thing is for these estimated levels of parameters, and this is of course true for anything, if I'm ever in a situation that would trigger the mixed strategy equilibrium in the auction stage, it would mean that I'm at risk aversion levels, going back to this previous picture, that are over here to the right. So the only way that my data would match up is if I saw mixed strategy entry in the auction and 0 revenue in the sequential mechanism, which of course we don't observe. So theoretically, we think risk aversion is not likely to be a driving factor. Matter of fact, one of the things we did, as I mentioned earlier, we got compelled to run a Holton-Lowry risk aversion elicitation exercise by, guess what, a referee. And so we did it and looked at basically the number of safe choices as sort of as an ad hoc measure of risk aversion. Just briefly pointing out, it doesn't have any bite in our data. So more risk-averse subjects don't appear to do anything differently in our data. So, we don't think risk aversion is playing a big role here. Certainly, if theoretically tells us it's inconsistent with the behavior. So the question is, what next? Right? And there's, of course, a number of ways to go. I got about 15 minutes, right? Or 10 minutes, I guess, since beer. Am I standing in the way of beer, or just, is it beer?
We have loss aversion.
Beer and wine.
Okay. Okay. Well, I want to know because I might go for 20 minutes if it's just soda. Right? So there's lots of ways to go. One thing you could look at is that so we've talked about a very particular. The model that Buelow and Klemper are using, and of course we're using up to here to predict behavior, is a very specialized equilibrium of which, heck, I still have to spend on. I don't really. I know what the D1 refinement is, but try to tell me how to explain it to my students. Is a whole other story. They're relying on a very particular equilibrium concept with a very particular equilibrium refinement strategy. Maybe one way to model this is not sort of non-equilibrium, I don't like that term, but other ways of modeling equilibria, such as quantum response type equilibria, cognitive hierarchy sort of equilibria, are perfectly possible ways to explain our data. Our model bears some similarities to quantum response. So, a quantum response equilibrium here would say that given the equilibrium that was described, bidder 2 should be exactly indifferent between entry or not. A quantum response prediction for that would always be that it's a 50-50 chance decision to enter, right? Because for any two things that give you the same expected payoff, you should basically randomize between. Quantum response might have a role here. Matter of fact, our model has some certain similarities to a quantum response in effect, something like a quantum response type strategy, although you'll see quantum response would not really explain the data that we need to do. Let me explain another model that's recently sort of was concurrently developed to ours, which I think is actually a nice complement to our experimental papers. Roberts and Sweeting have a paper that looks at empirical data. I can't remember what it's for. I think it's timber auctions, if my recollection serves correctly. And they basically show there that just as we observe experimentally, they show empirically that the revenue ranking of a sequential mechanism versus an auction are flipped. And they propose a model of what they call noisy value signals prior to entry. So you don't really learn your value until you enter, but you get a noisy signal of it. Okay? And given that you get a noisy signal of it, they show that it flips the results of Bueller and Klemperer. We're going to, given in our experiment, we didn't obviously give them any kind of noisy signal of their value. It's not likely to be happening in our experimental data. We propose sort of an alternative model, which has certain similarities in operation to that of Roberts and Sweeting, which we'll call noisy costly entry. Okay? Let me explain to you the idea behind it. This is sort of easy, is that we told them there was a cost of entry of a sixth, or of 10 cents, or 3 cents, or whatever it might have been, is that imagine that in the local lab, and probably in practice as well, there's some idiosyncratic, presumably unobservable cost of entry in learning your value. It doesn't. Right? So, if I'm thinking about, why is it that that Google entered and decided to bid on Yahoo? Well, we know kind of what due diligence costs, but on the other hand, we don't know what else is going on within the firm, and there might be other cost elements. So, heck, they got a whole division of employees, got nothing better to do, so let's go bid on the firm. Right? In our experimental subjects, I think there's lots of things that that'd be like that. And going back to issues of I want to make sure I keep that 20 units for not participating because I want to have beer money. Right? It's really costly for me to enter and risk losing that because I really like drinking beer. Right? Of course, we don't know that. In the lab, we don't have control over that. And of course, presumably the other subject doesn't necessarily. Well, perhaps. So we're going to add some unobserved cost of entry. This could look, matter of fact, if this was a mean zero cost with some noise, right, this would generate very similar predictions to a quantum response equilibrium. Right? On the other hand, we're going to allow that noise to be normally distributed with a potentially non-zero mean. So it might be that some people just like entering, that they view entry as being a good in and of itself. Right? We can think about this as a joy of competing story, although I caution it's not a joy of winning one. Right? So there's been some models in the theory literature that say, well, people will bid up because they really want to win. Notice here, we know that in the auction, right, once they get in the auction, they don't bid above their value or anything like that, which a joy of winning model would predict. Right? So this is just, hey, I don't want to sit there in the lab and not participate, because that's kind of boring. Right? I want to enter and get some chance to play. It's fun to compete. Right?
By the way, do subjects play both type of mechanisms?
No, they only participate in one. So that's the model we're going to propose. Of course, the critical thing is that it's only going to impact the entry decision and the preemptive bid levels. It's not going to, because all these costs, this cost too is a sunk cost at the time of participating in an auction. Once I get to the auction, we're going to bid as expected by theory, which is of course something we want to do since we know that that stage is remarkably consistent with theory. Right? Now, admittedly, I bid a little critical in some sense of the equilibrium concept. So in the effort of a modeler to change only one thing at a time, I'm going to still use the same equilibrium concept as Bueller and Klemperer. So I'm going to assume the same level of rationality and the perfect sequential Bayesian equilibrium with the D1 refinement that Bueller and Klemperer used, just with this one added element, that there's just some idiosyncratic noise that I don't know. And that noise might be very, 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 very small. Okay? So what happens? So in the auction, it's fairly easy to see that if you, of course, have a high enough noise cost of entry draw, you might say, forget it, I'm not going to enter this time. Okay? So, of course, it induces some small probability of not entry in the auction, just simply because you get some idiosyncratic costs. I've got something better to do, save my beer money. Okay? In the sequential mechanism, it's a little trickier. Turns out now that these cutoff type equilibria are no longer equilibrium. And here's why, right? The reason the cutoff equilibrium, this sort of either I preempted bid at P star or 0, was an equilibrium before, because there's no reason to go beyond P star as a high valuing first bidder, because what was it going to do? Buy you. What was it going to buy you anything, right? Because entry was already 0, so any bid above P star was worthless. Well, here, of course, small increases in your deep preemptive bid will always have a measurable impact on the rate of entry by the bidder 2s. So it's pretty straightforward to show that the only and the unique equilibrium bid function by bidder 1s is now a revealing bid function. In other words, it's an increasing function of my value, so of course, in theory, I know once what the preemptive bid was, I know what your value is, probability 1. Okay? So the equilibrium has changed dramatically as a result of this small noise term I included in the idiosyncratic cost, in the cost function for the bidders, and even arbitrarily small noise will make the step function equilibria disappear and only emit the unique equilibrium of a revealing bid function. Okay, it turns out you got to solve this differential equation that we of course take some checking to make sure that it's the right that it's unique and satisfies second order conditions, differentiable, all that kind of good stuff. But in this case it does. Here, let me show you, of course, what we want to do then is to see how our data matches up with this. So that's exactly what we do. Let me show you the basic results. So we basically use maximum likelihood results to sort of estimate these mu and sigma terms. So remember, mu, if it's positive, means on average bidders are getting a little positive benefit from participating. It's a sort of thing with a joy of competing. If it's negative, it means on average they're getting a little cost, added cost of me. I don't really want to compete against anybody. And of course, sigma is sort of the measure of how variable it is. And of course, so we'll use maximum likelihood estimation to find the best parameters to fit our data. Let me comment on what we tried to do is to try to allow for heterogeneity sequentially. So if you really only want one parameter, that's the first one. If you're allowing, you could imagine that different contexts would induce different feelings of these sorts of idiosyncratic costs, so on and so forth. That's what we do here. Notice that even in this case, it's enough to induce the expected revenue flips that we saw. So one way to think about it is I think these are sort of the most interesting ones. If you want to fit the data, what's sort of going on here? So in the auction, the best way to fit the data is there's a slightly negative cost of entry. In other words, look, I know the other guy's in there. It's going to take some work to bid against him. Maybe it's not so much fun. Right? On the other hand, for the sequential mechanism, the best fitting entry is actually a quite positive benefit to entering, which one way to think about it is I know the other guy's in there. Right? They already put some kind of preemptive bid in there. I got to get in there and compete against them. Okay? At least that's what the data suggests. And of course, depending on how much heterogeneity you like. Let me show you the data. Admittedly, the fit's not great. It's not perfect. That's probably not surprising. This is our observed preemptive bid levels. Here's the theoretical bid function under our model that we estimated. As you can see, obviously, still bids are generally a little lower on the high end and stuff. So it's not, by no means perfect. On the other hand, it's certainly better than the step function predicted by Elo and Klemperer. And actually, the aggregate results end up being quite close to the predictions using our best parameter estimates. I want to be careful of tying myself to the mast here in terms of the model. We think it's an interesting model. We think it suggests in some ways to take it along with the Roberts and Sweeting model tells you one, I think, very important story here. Is that the normative predictions, in some sense, of Elo and Klemperer are reliant upon an extremely fragile theory. Which isn't necessarily bad if we're very confident that the theory is going to predict behavior very well. On the other hand, even small changes in a variety of directions reverse the normative, the aggregate predictions of the theory. And therefore, it's really pretty dangerous to make prescriptions about what sort of institutions one side should prefer over the other, given the relatively tenuous behavior of real subjects, both in the laboratory and in the field. Right? And our model is a noisy cost of entry model, which we think is actually particularly interesting. I would suggest though that it's quite clear in running these things and other signaling games is that we're still making a very strong assumption of people playing these signaling equilibria in a complex setting, which requires. Honestly, would you make those same inferences that the theory expects people to make in these sort of signaling games? So that really one of the things I think we need to understand better is how do people actually behave in relatively complex signaling environments? Because there's clearly an interest in signaling. There's some sense of signaling here. On the other hand, it doesn't follow the prescriptions of theory very well. Maybe we need to think a little bit more about what's the right kind of signaling equilibrium, or how do we model signaling in these sorts of games. So there seems to be some attempt to signal, it's just not what theory prescribes. And that's sort of one way of thinking about it.
Do people do calculations? I mean, did they have a sheet of paper and all that?
No, I mean we didn't. We didn't. I mean, would it have helped them? I'm doubtful that it would have helped them, right?
Other suggestion: you could actually use your data that you have there, apply a kernel estimator, and then see if the distribution that you fit is actually better than the normal distribution that you started out with.
Yeah.
Suggestions.
Yeah,
You might see whether the kernel estimated distribution fits better the equilibrium that you suggested.
Okay. Okay. I mean, I think it does. I mean, I'll have to.
You see what I mean?
I think I do, and I'll have to. The distribution of results.
Right.
Yeah.
You have these dots, so you
Yeah.
can just estimate the empirical distribution function. And you might see whether that actually fits better the equilibrium that you suggest than the normal.
Yes. And Andrew is the econometrics expert, and I'm not sure that he did it, but I believe he did. So I had that check with him, but certainly, I mean, and look, I don't want to. There's lots of potential models that might explain this behavior, and I'm always a little dubious because, of course, we're still relying upon a very strong notion of. On the other hand, signaling equilibria with the revealing bit function seem a little more. That's the thing. We know experimentally that sometimes signaling equilibria do very well, right? There are sender-receiver games that people seem to understand the signaling equilibrium quite straightforwardly and behave consistently with it. There are other environments like this where it appears that, at least the standard predictions of theory don't match up. And the question is which direction to go. Clearly solving for a quantum response signaling equilibria is, very, very hard because, that you have to solve the bid functions. Now every type would have a bid function. You'd be basically randomizing over a set of functions, which would make things quite difficult. But we think at least it's suggested of ways to proceed. And I think the bigger thing is that really be careful when reading papers like this as to trusting the normative predictions, which is really very much Elena's original argument, is that using these strong theoretical concepts to say that that's really what should happen in practice is quite dubious, I think. As we saw in the laboratory, in a controlled environment, admittedly not always very realistic, that the revenue results are flowed. Okay, that's where I'll end there since I'm actually 2 minutes late for being.
Well, I just only want to point one thing out. The Pitt graduate said, don't worry about the pencil and paper. This is Penn State.
They know it. Oh, no, I like the beer comment. I thought maybe that was the...
Well, are there any questions for Tony? No? Well, let's thank him and let's get out.